So good afternoon, everybody, to the first IQOQI Colloquium. This is an event that we want to have twice per year. And we will ask speakers to come and give a talk on quantum information and quantum optics, especially devoted for the so many researchers that we are here in Innsbruck doing physics on these topics. So in this sense, this colloquium is supposed to be a bit more specialized than the nice physics colloquiums that we have during the semester. That's why we want to organize these colloquiums in the semester breaks, namely in February and around September. And starting this series of colloquiums, we are very, very happy to start this series with Ignacio Cirac. So for those who don't know him, just let me briefly introduce him, even though it's not an easy job. So Ignacio was born in Manresa, very near Barcelona, and then he moved to Madrid, where he studied physics and did the PhD in the Universidad Complutense de Madrid. He got his PhD in '91, and right after that, he got profesor titular permanent position in the Universidad Castilla-La Mancha between '91 and '96. But during that period, he was actually very regularly visiting for very long stays, both Gila and a group of Peter Zola in the University of Colorado, as well as Innsbruck, when Peter was here, until '96, where he got a full professorship position here in Innsbruck at the Institute of Theoretical Physics, where he stayed from '96 to 2001. Until he was offered a research director position at the Max Planck Institute of Quantum Optics, as well as an honorary professorship at the Technical University of Munich, where he's ever since, since 2001. And during this period, he has been awarded and recognized widely in the scientific community. And from all the list of prizes, I would like to highlight four. For instance, in 2006, he got the Prince of Asturias Award for technical and scientific research. In 2009, the Frontiers of Knowledge Award from the Banco Bilbao Vizcaya Foundation. In 2010, the Benjamin Franklin Medal, and in 2013, the Wolf Prize in Physics. These last three were shared with Peter Zola. And as you know, his research is very broad. For instance, his group is typically divided in three areas, in quantum optics, quantum information, and quantum many-body physics. And his research is always very broad in the sense that he can do very original proposals and be very close to experimentalists, but at the same time also address very abstract mathematical problems. And you all know the proposals on the ion trap quantum computer, the trapping of ultra-cold atoms in optical lattices for quantum simulation, long-distance entanglement between cavities, and so on. Very proposals that we all know very well. But at the same time, in the last 10 years, for instance, and also a lot of research on quantum information theory, the quantum repeaters, and so on. And in the last 10 years, he has also been very interested in the theory of many-body physics, in particular in tensor networks, both for developing better numerical algorithms as well as to derive a theory to describe these systems, which is having a lot of impact. So for all these reasons, we are very, very happy to have you here, Ignacio. So thank you very much for accepting the invitation. And please, let's welcome this Ignacio.
Okay, well, thank you very much, Oriol. So it's a great honor to be here, giving this talk in this colloquium, but it's also a great pleasure to be here among so many friends and colleagues and collaborators. We just look at any place and I see, Rainer, Hans, Barbara, Wolfgang, and people with whom I have collaborated in the past. Peter is not here, but I saw him last year. But anyway, so I'm very, I think, very connected to Innsbruck because of many reasons. So it's always a pleasure to be here back again. And so when Oriol asked me to give a colloquium, so he told me that it should be a little bit more specialized than the natural colloquium. But I decided not to be too specialized because I think that then I lose many of the people who are here, and especially, he asked me to talk even about tensor networks, and I thought that it was impossible, it would be very abstract. So I prefer to talk about something much more physical, which combines a little bit the things that I like and that I have always been doing. So something maybe very theoretical, which it's a theoretical tool to develop ideas. something more related to some experimental proposals, but there is some idea behind, and it's related, I mean, even not very closely, but somehow to some of the wonderful research that was done here in the group of Rudy and Francesca and Christoph and so on. So the existence of bound states, many body bound states, or few body bound states actually in some particular systems. And at the end, I will go all the way to quantum optics and to start proposing things related to creating photons and entangling photons and things like that, which is also very close to my heart. And all of it is related to some experimental setups that have appeared during the last 3-4 years in several places. These are atoms close to waveguides. And this is a work that was initiated by many people. And in particular, I was introduced to that through Jeff Kimball and Derek Chang. So I spent 2 months in Caltech 3 years ago. And then they showed me the experiments, and I became very interested in what they were doing. And since then, we started a collaboration with these 2 people that this lasted till now. And so I report many of the things that I'm going to talk about have been done in collaborations with them. And then in our group in Garching, so we started also thinking about some of these ideas, and these are the people who have been involved in the research, especially Alejandro González Tudela and Tao Xi, who will be the main people who have done some of the things that I will talk about, and lately Vanessa Paulich and Jinghai Wu. So Vanessa is a PhD student, the other ones are postdocs. Okay, so let me start just with the experimental setup that we have in mind, and that triggered the ideas that we have been pursuing, and that's emitters close to material. So in quantum optics, you typically had in mind the situation where you have an atom that is levitating because it's trapped at an ion trap or trapped with some dipole forces. You put a cavity around, and then with that you can build repeaters like Rainer is doing in the experiments. And but now it turns out that people are able to do something quite different, which is to put these atoms very close to surfaces. And so why do you want to put an atom close to the surface? So then we'll say, well, then there will be an interaction with the surface, so this will distort the nice physics that is coming out from the atoms, so it will give rise to the coherence. But it turns out that this is not necessarily the case. So actually, it turns out that since the material itself is composed of many atoms, so the atom that you put close is interacting with these many atoms, and this interaction can be coherent and can be very strong. So can give rise to very strong coupling between your atom and the atoms that are there in this material. And if this material now using nanolithography or some modern techniques, then you can shape it in a way that also transmits light, so that it's light coming out. So therefore, you can couple this atom through the other atoms to the waveguide, and then have a very strong coupling with atoms with light. So it's a way of coupling atoms with light, which is very interesting. And there have been some experiments in the group of Vlada Muletic and Misha Luking, where they have seen that if you put an atom close to one of these waveguides that has a little bit of structure, then what is called the Purcell effect can be large. So the probability that the atom decides to emit a photon in the waveguide is much larger than the probability that it emits somewhere else. So it's a very good coupling to the waveguide. So they saw that how the photons are coming out. In the group of Jeff Kimball and Oscar Painter and Caltech, they have very similar setup. So they have here some dielectric with day shape in order to enhance this coupling of the atom, and then they can convince very much the atom to emit photons in the waveguide when they're excited, instead of emitting them somewhere else. And there are tapered nanofibers, and there are some other systems. So altogether, it's a new setup which poses theoretical questions, experimental challenges, but also new opportunities to reach regimes that you cannot reach with actual systems. And that's what I want to talk about. So I will talk about three subjects related to that. So the first one is a little bit abstract, and so it's a theoretical framework. So now this system allows you to study what happens when you have these atoms, and then you send photons through a fiber, so for example 2 photons, and you would like to know whether the atoms are able to expel these photons and have some entanglement in the photons. So if there's a good way of entangling photons, and how these photons will be maybe too entangled, because may not be entangled only in polarization, but also entangled in the orbit, and this will be bad. So that's something that you want to study. Or maybe you want to excite these atoms and such that they produce the photons, and the photons are the ones that are entangled. Or maybe you want to send photons through the waveguide and have some atoms excited in such a way that now the atoms are entangled to the photons that are coming out. And so this process actually gives rise to several questions, and so what we have been doing is to develop some theory framework to do that. One of them is very much motivated by quantum optics theory, so input-output formalism. So we have adapted input-output formalism to this system, but we have also imported some techniques from condensed matter physics, field theory methods, path integral methods, in order to solve some of these problems exactly without Born Markov approximations nor anything else. So this will be the first part of my talk. It will be very qualitative, okay? So I will not write almost anything. I'll try to explain what we are doing. The second thing is related to what I mentioned before. It's very well known for many years that if you put an emitter close to some waveguide, which has some dispersion relations, or where photons can propagate in this waveguide, then it may happen that your atom, you put initially your atom excited, so it may happen that actually this atom does not decay, so that it stays excited, even though one would think that the atom will decay and would emit a photon in the fibers, and sometimes it happens that it was predicted that this is not the case in some particular situations, and the reason for that is because there is a bound state. There is a bound state of an atom and a photon in such a way that the photon, somehow the atom is attracting this photon and the photon doesn't want to go away. So that's a prediction that was done back in the 80s, late 80s or 90s. And so what we have been showing is that actually in the same setup, you can have not only one photon bound state, but also 2 photon bound states, 3 photon bound states. So a single atom, a single impurity can have many bound states around it. And we have developed a theory to describe that. So I will mention that. And then we'll propose some experiments where to observe this kind of behavior. And the last part will be related to use this setup. So to use the fact that you have a very strong coupling in these systems of atoms to the waveguide modes in order to do something that is difficult with other setups. And in this case, the thing that is difficult will be to produce single mode, multi-photon state. So a Fock state with 22 photons coming out from your waveguide. Okay, so I'll start from the first part. This was done in collaboration with Tao Xi, Derek Chang, and the first part also with a group of Derek Chang. And so as I mentioned before, so people have made theoretical proposals on those systems. So what to observe, so how to entangle atoms here, how to deal with these situations. And so typically what they predict can be observed in several observables. So you can make a prediction and say, oh, let's look, for example, at the scattering matrix. So the scattering matrix describes what happens when I send something in and I wait for an infinite time and it's coming out. So it's the probability with the amplitude that if I send something in, that something will come out. For example, I can send 2 photons in with some momentum, and then there will be 2 photons coming out, but they will have different momentum, and maybe they are entangled, so they now have a superposition of different momentum, and this is described by this scattering matrix. And this can tell you whether, these photons will be entangled, or if the light will be transmitted, or you have to end ports, or if there will be transmission, etc., etc. Another quantity which describes some of the proposals in this context is related to atomic dynamics. So people have proposed, for example, that here there will be some kind of polaritons in which you have that the photon is somehow attached to an atom, and this photon can jump from atom to atom, and if you have 2 of this excitation, then may form even a molecule in such a way that they jump together. Okay, something that you may want to study, the atom dynamics, the existence of bound states of the photons, many-body behavior in the atoms itself. You can also study the photon dynamics, or now also propagation effects. So actually in these systems, if there's atoms, the distance between the atoms is sufficiently large, then you can see retardation effects. So typically in quantum optics, we don't see retardation effect if we do an experiment in one side, because the speed of light is so fast that the times of the experiments are very long in comparison to the time that the light takes to go from one place to another one. However, in these systems, it turns out that the speed of light can be very small, because you have some dispersion relation. Dispersion relation you can shape, and then you can have a group velocity which is very small, can almost stop your photons, and therefore retardation effects can be important. So it would be nice to have descriptions of this, which of this kind of phenomena. Okay, so that's typical scenario. So one has a set of atoms on top of this dielectric, this waveguide. And you have some initial state of the atoms, some initial state of the photons, which could be this Fock state for the photons, and some state for the atoms. And then you would like to study the evolution, and at the end see what is the probability amplitude of something happening at certain time, maybe a time infinite or intermediate time. But what is common in these systems is that you have, well, some Hamiltonian And that's the one that we use very often in quantum optics. So some Hamiltonian for the atom. So for example, this could describe some level structure of the atom that is complicated, some EIT kind of structure of your atoms. Then the Hamiltonian of the waveguide and the interactions, the dissipation, and and so the interaction between the atoms and the waveguide, or maybe some dissipation, so the interaction between the atoms and the rest of the electromagnetic field. And that's the problem that you want to solve. You want to predict what will happen under some initial conditions. And in order to solve this problem, as I mentioned before, we have developed two techniques. So one of them is what we call input-output, which is very much motivated by the typical quantum optics approach to that, in the Markovian limit. And the whole idea here is that by studying the atom dynamics, you can say not only what will happen to the atoms, but also to the photons. So you just don't have to care about the photons. You study somehow the atom dynamics, and then you can answer questions about the atoms and the photons themselves. And the second one is a path integral in which there is no approximation. And also the idea is that by studying the dynamics of the atoms, but it's a more complex dynamic of your atoms, then you can say things not only about the atoms, but the photons themselves. Okay, so to be a little bit more concrete, now say we have this problem with the atoms with some particular structures. So I will concentrate most of the time on structures, which is kind of this one a bit complicated, EIT. So there are some lasers interacting with the atom. There is the waveguide is coupled to some of the other transitions. I'll explain that later on, but that's the idea, that we'll have certain atomic structure. Then there is the waveguide, and this waveguide, as compared to what we study typically in quantum optics, in which we have free space, here we can have some dispersion relations. So the photons that propagate there, depending on the momentum, then they have different energy. There's the dispersion relation, and will depend on how it's the structure that you build here, and that's what they do in the experiments. They build some structure because they can design the dispersion relation. And using the dispersion relation, that if you look at here, then they will have no dispersion. So here is basically a line, a linear dispersion relation, so the photons will propagate without dispersion there. But if you go to the border, then the dispersion relation is very flat, so the photons will be stopped. So your transition frequency is close to the border, then the photons will propagate, or the photons that are on resonance with your atom will propagate very, very small. And there are many modes, so in a little bit of an energy window, in a very small energy window, there are many Ks, so there are many modes. So this is why you get the strong couplings there. There are many modes interacting with your system. And then there is the interaction in which, well, it's out of that, but anyway, so interaction is the typical that we want. So we have some atomic operators. So whenever the atom goes from excited state to a ground state, it emits a photon into the fiber, and there is a description of that. It's a typical description that we have in quantum optics. Okay, so the first method that we describe is motivated by the input-output formalism developed by Crispin Gardiner in the 80s. And it has several conditions. Under those conditions, then it will work. And if these conditions are not fulfilled, this will not work. So the first thing is that you take your linear dispersion and then you linearize. So you assume that the dispersion relation is linear. Not like here, which is not linear, but you assume that it's linear. So this will be true when the transition frequency of your atom, which is represented here, it's somewhere here in the middle, and the frequencies that are important in your problems of Rabi frequencies, decays, etc., are around that, and they only see this part of the dispersion relation, only the linear part. And in that case, then you will be able to represent the waveguide by a linear dispersion relation. The other approximation is when you have a flat coupling constant. So somehow all the atoms are coupled in the same way, basically, to the waveguide. So there might be phases depending on the position, but basically a flat does not depend on K, on the momentum, and that's the second approximation. And the third is that you neglect retardation effect. So if a photon emits an atom emits a photon into the waveguide, then the time it takes to go to the other side, to some other atom, it's very short as compared to the time scale at which this atom changes. Okay? And then you can neglect retardation, and you put these things together, and you can derive this theory. And at the end, what you get is an equation for the atoms, where there are only the atoms, the master equation. If you have some, I told you before, some initial state in the waveguide, so you have photons that are coming in, a Fock state, 3 photons, then you will have to put in your master equation for your atom some terms, which will tell you that there are photons. And if you want to represent Fock states, then at the end you'll have to do some exercise. You'll have to solve the equation and do some kind of functional derivatives, which is relatively simple. And if you want to study not only the evolution of the atoms, but that of the field, then you will have to do, a couple of Fourier transforms. And at the end, you will have. So at the end, there's a typical formula for some scattering matrix. So the amplitude that photons with momentum K1, K2, up to Kn go out after an infinite time with momentum P1 to Pn will be given by something that you have to evaluate, Fourier transform and so on, and that's something that you can do in practice for many systems, as long as you don't have too many atoms. So at the end, I mean, you can do this for 10 atoms or 12 atoms or 5 atoms, or you have few excitation maybe to 200 atoms, so the limitation here is on the atoms, not on the photon side. Okay, so these are 2 examples to check. So now go to physics. So we go to a physical problem and investigate this with that. So what is this physical problem? So we have 500 atoms. And these 500 atoms have this internal structure. So you see there are 2 hyperfine levels and 2 excited levels. And there, well, actually it's 1 excited level, sorry, this one here. And these 2 are coupled by an external laser. This is this omega here. And this transition here from E to G is coupled to the waveguide. So you start with your atoms initially in G. And so nothing will happen because there is no photon in the waveguide. Initially there is no photon in the waveguide, so they will stay there. But if there is a photon in the waveguide, then they can come here, and then in principle they can come down. But we know from the EIT, from electromagnetic induced transparency, that if this intensity of this laser is very strong, then actually this will create some kind of splitting of the levels. And now, if the frequency of the waveguide is exactly in the middle, then there will be a transparency window. So you send some photon through the waveguide that would be absorbed if there is no laser. Now you put the laser and shift the levels away, and then the photon can go through. That's this electromagnetic induced transparency, the phenomena. And this depends on many things, but depending on the intensity of your laser, then you have a transparency window which is broader or is thinner. And so here what we did is to study in this system this situation. So we assume that we have all the atoms in the ground state except 1 in the excited state. But actually what we have is like a spin wave. So we have a linear combination of having this atom in the excited state, or this atom, or this atom, of this atom, of this atom, with a Gaussian profile. So it's like if we had some spin wave in which we put some phases to give some momentum. And in principle, this spin wave that is inside will be coupled to the waveguide, and then this could just move there and propagate along that. That's what would happen in the ideal case. But now what happens, we put in the frequency, so let's say the transition frequency corresponds to this frequency window. But if this superposition is very narrow in space, it means that this corresponds like a pulse. You can think of a pulse that is very narrow in time. And so it will be very broad in frequency, and it's very broad in frequency. It will not fit in the frequency window, so it will be absorbed. It will not quit transmitted, and this is what we see. So it's propagating to the right, and after some time, it's absorbed. And on the other hand, we start now also with a linear superposition, a spin wave, but it's very broad in position. It will be very narrow, will be very broad in time, very narrow in frequency, now can fit in the frequency window, and that's what you see, that it propagates without absorption. That's a kind of check that things work well for the method, and you can calculate these things very efficiently and very well. We can take another problem now in which you have 2 atoms, two excitations. So you send 2 photons in, and now you have 200 atoms in this case. And now the atoms can absorb the photon, you can absorb the photons, but they can interact among themselves. So actually, what you do is that you include the fact that this could be a Rydberg level, and then there could be Rydberg interaction among the atoms. So you include the interactions among the atoms, and now you see what happens when you send the atoms through, depending on the interaction between these 2 atoms. And then you will see, well, things that can be understood very well. So if there is no interaction, then 1 photon goes through in the same way that 2 photons will go through. There will be some anti-bunching or some bunching. And if the interactions are on, then actually this frequency window, when 2 atoms are in the excited state, because of the Rydberg interaction, is shifted in frequency. So what it will mean now is that the atoms will not go through unless they have a frequency which is different from the original one to match this Rydberg interaction. So, I mean, I don't want to enter into the detail of physics. This is, just an example of what you can solve with this method. And in those problems, the conditions for this Markov approximation are fulfilled, so these should be problems that you can understand and study with this method, which at the end, it turns out to be very simple. Okay, so we have studied also entanglement generation, so what happens when you send 2 photons through, and they are coming out, whether they are entangled or not in polarization, or they are entangled in orbit, Rydberg, and also dipole-dipole interactions, different kinds of interactions, excitation probabilities, etc., etc. But that's not the point of the talk now, so it's just to tell you about a little bit the method. Now let's go to the second method. The second method does not make any assumptions, so the dispersion relation can be arbitrary, interaction can be arbitrary, and the distance between the atoms can be arbitrary, so there are retardation effects. And now it's much more complicated. So now you cannot adapt the methods from quantum optics and describe this with quantum optics. In quantum optics, we always trace the electromagnetic degrees of freedom and do a couple of approximations in order to get the master equations and quantum progression theories and so on, and that's what we used before. So you cannot do that here. So what do you do instead? Then you go to condensed matter physics, and you see that people in condensed matter physics actually have studied things that are not exactly the same. They study things in thermal equilibrium, so imaginary time. But I mean, you can translate and get an idea of how to solve these problems now. And here is a little bit of the idea, I mean, just in 2 words. So first of all, you write everything as a path integral. So you know from, you have a time evolution, e to the minus I ht. You can cut times, e to the minus I ht. You can trotterize. You put the identity in the middle. And then the identity is like an integral, and so you have now many integrals. These integrals in the continuum go to a path integral. You do this, and so this typically looks like that. So some evolution from some initial state to some final state with some Hamiltonian looks like an integral in which there are the atomic degrees of freedom, there are the electromagnetic degrees of freedom, and this S is an action which is like the Hamiltonian for the atoms, there's the Hamiltonian for the fields, and then the Hamiltonian for the interactions. And then you realize that actually the Hamiltonian that we have, the basic Hamiltonian of quantum optics, it's only linear or quadratic in creation and annihilation operators of the electromagnetic field. So you remember it was something like A daga A or A daga times operator. So an operator you can only annihilate one photon at a time, right? And so this means that these functions here are quadratic in these coefficients alphas, basically. But if you have quadratic functions, this means that these are Gaussian. And if it's a Gaussian, it turns out that you can do this integral. You can do path integrals with any Gaussian function. So you do these path integrals, and then at the end, you get only a path integral for atoms. So it means that you have a problem now only for atoms, which is exact, and that you can try to solve. I mean, the problem has a little bit of detail, so now it has kernels, so time dependent, but at the end it's a problem for atoms that you can solve. So now you can solve this problem and try to go beyond what we said before. And so, for example, we studied now what happens now. You have 2 atoms, both of them in the ground state, separated by some distance here. And you look at the reflection coefficient. So you send the photon, and you look at what is the reflection coefficient from that. And if the atoms are close together, there will be no retardation effect. And then what happens is that basically, as long as the distance of the atom is a multiple of the wavelength, so 2 pi times the wavelength times an integer, then the reflection coefficient, I mean, will be just depend on the momentum only, but you will have this curve, so independent of the distance. So this is why this blue and red curve are the same, because you change the distance and nothing changes. But now you go to very big distances, and then there are retardation effects, and then indeed that this changes a lot. So actually what happens is that these 2 atoms behave almost like a cavity. And this cavity, the photons have to propagate from one place to another one. There are some resonance, some interference effect, and this is why you see that, I mean, there are some zeros here. So reflection coefficient at some point is 0. So everything is transmitted, something that doesn't happen with the theory before. Okay, so the theory that I represented before, the ones that we use in quantum optics, will give rise to curves like that and will not reproduce curves like that in which retardation effects are important. And the same thing you can do now. You start with no photons coming out, one atom excited, the other one in the ground state, and you wait. What will happen? Well, at some time, there will be some probability that this atom is excited. That's what is represented here. That's the time. If the atoms are very close together, then nothing will be seen. But if the atoms are far away, then it's the time where this will be 0, and then there will be something coming out, probably. But this 0 is 0. I mean, it's not 0.000000001. I mean, it's exactly 0, because, I mean, this is including retardation, and you see nothing propagates faster than the speed of light, so it has to be 0, and you get that is 0, something that you will never get with a Markovian master equation. Okay, so I finished now the first, more abstract part of my talk. I'm going now to talk about this multi-photon bound states, and that's a work that we posted in the archive very recently. And so what I'm going to talk about? Well, that's what I mentioned before. No, you have an atom also close to some waveguide, which has been structured in order to shape and to have some special dispersion relation that you can engineer. And what these people, John and Wan, realized in 1990, that if you just write this model, so an atom coupled to a waveguide with some dispersion relation, then that there might be some bound state. So some photon doesn't want to go out, even though one would think that the photons have to propagate down the fiber. And so you will have a state, a bound state, which is a superposition of having an atom in the excited state and 0 photon in the fiber, and 1 atom in the ground state, and 1 photon in the fiber, which is surrounding the photon, doesn't go away. And so what is the interpretation behind that, which is very clear? It's just what can be understood in some limit. So imagine that this is the dispersion relation that you have, and that the atomic transition is very far from resonance from any point at the dispersion relation. So it's in the band gap. So this means that if you start with an atom in the excited state and has this energy, and you wait for some time, and you would expect that the atom would be in the ground state and a photon would go out, this is impossible because energy would not be conserved. Because at the end you will end up with 1 photon here, so you will have to have this energy. The atom will be in the ground state, so this energy. So energy cannot be conserved by that. Because we know this energy conservation has to be taken with a grain of salt, because the interaction itself gives rise to energy. And this interaction, I mean, makes that things don't look really conserved. No? But this interaction energy can be so small that cannot cope for this difference of energy. And that's the idea, that you can have an excited state that doesn't decay. And a way of understanding that the excited state, because of energy conservation, does not decay, is that indeed there must be some bound state, a linear superposition of ground state, maybe with a lot of population in the excited state and little population in the excited state, that is an exact eigenstate of your problem, and that's exactly what it is. Now what is funny is that if you go closer and closer and closer of resonance, then this eigenstate survives. And even if you are in resonance, then this eigenstate survives, and so you can still have an linear superposition of excited states and ground state, and still your photon will be like not going away. That's a phenomenon that I mentioned before. Yep?
Yeah, but you don't have a vacuum.
Okay, so of course, if you have now, well, this is a bath, but this is one of the baths. In this bath, there is no decay. In the exactly, there will be the electromagnetic fields of freedom, the ones that are not in the waveguide, and since they don't have this structure, this dispersion relation, then it will decay there, so eventually this will decay, and that's the reason actually why this has not been observed experimentally, okay? And that's this what I mentioned here. Okay, it has some consequences, so in fact, this bound state of an atom and a photon means that there is some photonic mode there, which is very relevant in the coupling of the atom. So the atom is very coupled to one mode of all these infinite modes that are there. And so now you put another atom here, then it can be coupled to the same mode, and then this behaves like a cavity QED, because you have a photon mode, an atom, another atom, and then it can start exchanging photons. So it's like having two atoms in a cavity. And this has been described, for example, by Derring Chang and some other people in order to propose ways of coupling atoms and in a coherent way by using that. And so some time ago, actually, we knew about that, and so we proposed an experimental realization in which this could be observed, so nobody has done it, but it's based on atoms in optical lattice. I'll talk a little bit about that later on. So in principle, it's possible to observe all these phenomena with a setup which has nothing to do with this optical setup. It includes only atoms and optical lattices and nothing else, and it's relatively straightforward. But anyway, so what I mentioned before is that we have been what we realize is that when study this problem is that there are some other bound states that you can identify and you can find them. And so there are states in which you have a superposition of the atom in the excited state and n photons around, plus the atom in the ground state and n plus 1 photons around, and they don't escape. Okay, so in the same problem, there are other bound states. And a way that I will explain in a second, so of interpreting that, is that from the point of view of the photons, the atom is like an impurity that is there, that is modifying this dispersion relation in which the photons can propagate. All of a sudden, they see that there is something there. And this something can create a potential for the photons. A potential. And it turns out that it creates a potential that is attractive. So the photons see an attractive potential, and now since the photons are bosons, they can condense there. So there can be 1 photon in this potential, or 2 photons, or 3 photons, and they correspond exactly to these bound states that we found. So we want to explain that a bit more in detail, and say that what we did is that we found an analytical approach to solve that, and so identify what are these wave functions, and then we observed some funny behavior. So for example, non-perturbated, so things that you can never describe with perturbation theory, and we used some DMRT methods in order to check that our ideas are right. Okay, so there are some other papers that have been observing some kind of bound states in the system. So 2 photons bound states actually were known, okay, in this setup and already some time ago. And other one-dimensional models, people have also seen bound states. And so basically, they are models without rotating wave approximation. And when we posted the papers and some other related work by Peter Ravel and Derek Chang also appear, and they also found some other bound states, like this one here. Okay, so we go a little bit into detail. So it's again, so for the ones who like to see formulas, there's the system that one has a 2-level system, a very simple structure, 1 electron excited, 1 ground state. And that's a Hamiltonian. So the Hamiltonian is the atom can be in the excited state in the rotating wave approximation. So they appear here in the rotating frame at the tuning. So this would be like the detuning from the top, from the bottom of your band, this delta. Then there is the photons can propagate in the fiber. So that's the linear, this dispersion relation that is here. And then there is a coupling between the photons. So every time that the photons go from the excited to the ground state, it emits a photon in the fiber. And as I mentioned before, so what you want to do is to find eigenstates of this Hamiltonian and to find that there are eigenstates which in the thermodynamic limit, when the size of your system goes to infinite, these are proper eigenstates. So these are normalizable wave functions. That's what it means a bound state. And so you do that, and then you find them, and that's a little bit the kind of the phase diagram of this problem. So we see all the regimes that you can study. So for example, this is the detuning. It represents the detuning of the atom. So that's the detuning from the top and bottom of the band, and so it can be positive or it can be negative. Then we have another parameter here, which is what we call this omega. This omega is the coupling constant between the atoms and the waveguide. Okay, so I mean, 0 it means that they are completely detached, and omega going to infinity is a very strong coupling. And then we have a bandwidth here, and this bandwidth is which goes from here to here. For example, is this region corresponds to being. This would be on the bottom of the band. This would be on top of the band, and this would correspond to being in the band. And so now you look at this diagram. There are some regions which can be understood very easily without thinking too much. The first is what happens if we just take the tuning equal to 0 and take this coupling going to infinite, very, 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 very large. So what will happen is that the atom is coupled somehow to the atoms that are in the waveguide that are close to this atom and very strongly. And so, I mean, you can see that this transforms into, I mean, this model that I wrote transforms into the James-Cummings model. And in the James-Cummings model, we know that there are bound states. So there are eigenstates, which are linear positions of having one atom excited and n-1 photons, and one atom in the ground state with n+1 photons. So there are bound states here. So it's very clear that here there should be bound states in this limit, and these, which are very localized around the, actually they are on top of the atoms, let's say. Now, we can go also to the perturbative regime. So when we make delta very large, or delta positive very large, as I mentioned before, and when you take delta very large, what you can do, I mean, you know, in quantum optics, you can arithmetically eliminate your level. So it means that your atom will be in the excited state plus epsilon times in the ground state, if there is a bound state. And then you can do a perturbation theory with respect to the epsilon. And then what you find is an equation for the photons in which you have eliminated the atom. And this equation in the photons represents what I told you before. So the photons can propagate, but all of a sudden they see an impurity which creates a potential for the photons. And this potential is like a delta potential. And delta potentials have always one bound state. And that's the bound state where the photons can condense. So in this region, and in this region, you can understand that there must be these bound states. And then if you go to the other regions, then you say, well, let's look for something that, I mean, some wave function that would describe the physics, and then you make an ansatz. And this ansatz is represented here. So you have a linear superposition of being in the excited and the ground state. And if you're in the excited, you have n-1 photons. And you say, well, maybe they are in the same mode. But this is what will happen if they would condense. And if they are in the ground state, maybe n-1 are in the same mode, and 1 is in a different mode. Okay, so I mean, this doesn't come from the brain. So of course, you do some numerics, then you learn, and then you realize that the Schmidt decomposition has only 2 terms, or has almost 2 terms, and then you realize that this is the solution according to that. So what happens in this other regime is that this idea of eliminating the atom giving rise to a potential for the photon cannot be done because there is no perturbation theory. But what you can do is somehow hybridize your atom with some local mode. This is mode B. And this behaves now at an impurity for the rest of the photons, and the rest of the photons see now the creation of a potential created by the atom and the photon around, so by this impurity. And I mean, this is what you see, what you do, the calculations with that. And then you can have condensation in that state. So it's a very much more complicated condensation. And in fact, you see that you cannot get any by perturbation theory. It's a non-perturbative behavior. And the way that you can see that in this region here, so when the coupling is very strong and the tuning is very small, but the coupling is still not in the James-Cummings model, but is somehow in the middle, then you can see that it's non-perturbative because you can plot things like the energy of 3 photons, this 3-photon bound state or the 4-photon bound state, as a function of the coupling when the coupling goes to 0. And you see that it decays like, for example, omega to the 4/3, which is not, so it means that you can never get it with perturbation theory, no? Because in perturbation theory you get something like omega squared, omega to the cube, but not to the power 4. It's a non-analytic function in omega. And so you see that there is a non-analytic behavior, and these red lines and the blue lines, the continuous lines, the dots that you see here is for a problem in which we solve it with the MRG. This is an exact calculation, basically, numerical exact calculation, and the lines are the ones that are coming from our model. So we saw that with our model, we cover the whole spectrum, that this describes the physics not of the whole spectrum very well, and gives rise, even analytically, to these 4 sets, et cetera, et cetera. So I think that we understand very well this model. And we also look at some other properties like the local. So how big is this photon? How fat is this photon? Well, it depends on the coupling, so you can understand it. You take our model, and then you can predict how fat it is as a function of the coupling strength and the coupling of the parameters. And this model that I gave you before will give you that in a very. And you can do it analytically. So at the end, actually, you have only 3 parameters that should describe the whole phase diagram. Okay, so. And that's now how to do this in practice. So the problem with the setup of an atom coupled to a waveguide, of observing that, is that what you say is one problem, that actually this atom will emit somewhere else, not in the waveguide. And on top of that, these waveguides are lossy. I mean, when you put a photon there, it will be absorbed by the waveguide. So the lifetime in the photon in the waveguide is very short. Of course, they go very far because they can move very fast, but still is very short. So that's why you cannot do that. So this is why we thought of an alternative way of seeing that, and this is with atoms in optical lattice, and it's based on this paper that we wrote some years ago, proposing to observe superradiance of atoms, so superatomic radiance in superlattices, in atomic lattices, and you'll see that it's very simple. So now forget about photons. There is no photon here. I mean, there will be lasers, but there are no photons. Okay, so there are not going to be photons. So now, instead of photons, there will be atoms. So when I have one atom, it will represent that, what before I say that I had a photon. Okay, so they're bosons, so these are bosonic atoms, so this is why they can be the same. And then these atoms have 2 internal states. So internal state that I call A, and internal state that I call B. And both of them see a potential, which is different. So for internal atoms in A, then you have usually a lattice, a normal lattice, like you have in atoms in optical lattice. And for the atoms in B, you have a different lattice, which here is exaggerating and saying it's just a single side. But in principle, it could be a different lattice where there is no tunneling. So these atoms cannot move here. So they're frozen if they're in internal state B. And this is why they see one potential corresponding to one lattice side where they're frozen. And in the other internal state, they can move in the fiber, in this optical lattice. Now, of course, if you design a different optical lattice, you take lasers in different directions, you will be able to design different optical lattices. So this is how you could change the dispersion relation and how you indeed change the dispersion relations for atoms in moving in optical lattice. So you can design, in principle, this dispersion relation in the way that you do with atoms in optical lattice, while you're choosing the properties of your laser, the directions, the intensities, polarizations, or whatever. And now the idea is just very simple, just to use a radio frequency or a Raman transition in such a way that this atom can come from this level to this level. And the promise is that if you have something like that, the model that describes that is exactly the same model that I told you before with the translation. Photon is now an atom in level A, and what before was an atom was an emitter, and could be an excited atom or a ground atom, atom in the excited state or atom in the ground state before. It's the presence or an absence of an atom in this internal state. And you can see it very easily. So let's look at the Hamiltonian. Let's see that the Hamiltonian that describes is the same as before. So if you have an atom, well, actually, you should call this 0 and this 1. So you have an atom in 1, then you have some energy, which is different. This is this delta in the rotating frame with respect to this laser. But this is this delta, 1, 1. You have one atom, then you have some energy. Now you have, the atoms are in level A, then they can propagate, and they will see some dispersion relations. So this will be the description of non-interacting atoms just moving here. So epsilon k, a dagger k, a k, the same as before. And now, when one atom disappears from here and goes to the other internal level, what happens is that from the state of having one atom, go to the state of having 0 atoms. And at the same time, I create one atom in level A, in the internal level A. So this appears one atom in B and appears one atom in A. So this is like an 2-level atom interacting with an electromagnetic field. It's exactly the same Hamiltonian. The only thing that I'm using a kind of a mixing notation with first quantization, second quantization, but if you write it in the right language, then you see that this is exactly the same problem. So in this problem here, then you will be able to see these bound states, and you will be able to see all these bound states, and on top of that, you will be able also to see, since this is the same Hamiltonian that appears in QED, so phenomena from QED, for example, superradiance and many other things related to that. And this is what we proposed some years ago. But in this setup, it should be possible to observe this existence of these bound states, the ones predicted, 30, 25 years ago, and the ones that we predict. OK, so how am I doing with time? OK, so then I'll talk very briefly about these multi-photon sources. That's a work together with also Derek Chen and Jeff Kimball and Alejandro and Vanessa. And so, so the idea here is how to build some multi-photon sources. And so for the moment, so you read in the papers that there are people doing experiments with a single photon, or maybe with 2 photons, with 3 photons. They have been experiments up to 8 photons. And the way they create these 8 photons is typically by parametric down conversion. So they create pairs of photons at random times, let's say. And now it may happen that these 2 photons which are created here and the 2 photons that are created here are created at the same time. So now you have 4 photons, and you start putting beam splitters. You can entangle them. And you have another source, and you create another photons. Maybe these 2 photons also come at the same time, so you can have 6 photons. And if you have another, then it can happen still that their photons come at the same time. So you'll have 8 photons. But you see the probability of that n photons come at the same time scales exponentially with them, because it has to be at the same time as this and this and this and this and this, and n probability is a multiplication. So this means that if the probability of getting a photon on some period is, let's say, 0.1, then after 10, there will be, 10 to the minus 10, which means that it's hard experiments. And in fact, experiments where people were able to reach 8 photons, it took days just to have a single click in the detection. Okay, so that's a problem. So the idea here is, can we have a photon generator which would not have this exponential, or that would scale much more, and for example, it's realistic, or at least from the theoretical point of view, realistic, this in principle to have 20 photons, 100 photons, okay, with a probability that is not that bad. And that's what we have been working. Of course, an alternative would be to use what Rainer is doing in the lab, putting atoms in a cavity, exciting them. But that's using these emitters in photonic structures. And the idea is that you here can take advantage of the strong coupling of the atoms to the photonic waveguide. So the fact that they are coupled, so they emit photons in the waveguide and not somewhere else, like in cavity QED. But on top of that, we will use collective effects. So the fact that you have many atoms, then you can get enhancements which are factors of n if you have n atoms. These are collective effects, no? Like the ones that appear in superradiance. Okay, so I'm imagining the same setup as before. We have now more than one atom here that is coupled to this wavelength, strongly coupled. And I'm going to assume that the transition frequency, these atoms have a very simple atomic structure, excited state and ground state. And the transition frequency, let me assume that is in the band of your band structure. And in fact, it's close to the band gap. And I want to be close to the band gap because you see, as I mentioned before, here you're getting close to the band gap, your transition frequency is here. In a range of frequencies of energy, there are many, many modes. So the density of modes is large, and when you use Fermi golden rule, the probability of spontaneous emission there is proportional to the density of modes. So if the density of modes is large, then the probability of emitting there would be large. And this is what gives rise to these large Purcell effects, which is defined as the rate at which we might emit in the mode at the rate that you emit out of the mode. So at the moment in experiments, I think that people have reached something like a factor of 5, but the predictions go up to factors of 10,000 or something like that. That's the main motivation of starting these experiments. So assuming that this P1D, this Purcell effect, this probability of emitting is large So what can we do? Well, so one possibility that you can do, you want to generate exactly M photons, would be that you take 5 atoms, you put all of them in the excited state, and then you wait and you let them decay, and then they will emit maybe 5 photons in the waveguide. And so what will be the error that you will have? Well, it's very simple, that it would be, I mean, it's related to the probability that they are going to the waveguide. This is why this Purcell effect appears here. It's proportional to the number of photons. So the more photons there were, the more unlikely, no? Because all of them have to be here. So actually the error goes like m divided by this p. This p is a large number, okay? So this p should be, I mean, this 20, 100 maybe. And so you see that this infidelity, so the error may be small. The problem is that in these photons that will be coming out will be completely entangled with each other. So the photon, you can do the calculation, actually using the formalism developed at the beginning, you can do the calculation, and then you can see that this would be not a single mode state, this would be M mode state, which will be very entangled, will be very dirty. So you put these things in a beam split and you take another photo, you will not see any interference at all. So that's very dirty. So that's the main problem. So how can we get clean photons, single mode photons now, but with high probabilities? And the idea is to use these collective effects. So the idea is that now if we have many, many atoms, like n atoms, then this Purcell effect can be enhanced by a factor of n. And some time ago, together with Diego Porras, we showed that if we put m excitations, few excitations here, 20 excitations in 100 atoms, then you will have a single mode coming out. So all these 5 excitations, the collective effect will make this to be a single mode where the errors goes like 1 over n, the total number of atoms. So this is why it will be very clean single mode. So the idea is to do that. Then to have many atoms, create few excitations, but this has to be collective excitations. And then once these are created, then just release them and then let them go through the fiber, and this will give the desired state. Okay, so that's a little bit the idea. So first, you'll have some internal structure in your atoms. Okay, so maybe most of the atoms are in this state S that I'll call here. So these are 2 hyperfine levels. These are an excited level. So most of the atoms are here, but in the loading scheme, what you will do is to create several collective excitations. Collective excitation means that you have 2 atoms in the ground state and the rest in S, but you don't know where they are. So it's a linear superposition of all possible positions in which these 2 atoms can be. It's like a W state with 2 excitations. And so you create something like that. And then once you have created that, then you're done. Because now, if you put a laser here, then you will excite these atoms. And now there will be a collective effect, a collective phenomenon related to superradiance in which these atoms will emit photons in this transition. And the coupling to the waveguide will be n, the number of atoms, not the number of excitations, but the total number of atoms times this gamma, and this enhanced gamma already. So that's the Purcell effect will enter here for the probability. So we'll have very little error. And okay, so the question is how to prepare these collective excitations on this system, because these are highly entangled states. And so, I mean, the simplest way is to use that. So together with Peter and Misha and Lumin, when I still was in Innsbruck, we proposed this method for quantum repeaters to create entangled states between distant nodes. So you can just translate basically this method in the following way. So imagine that you have your n atoms here, and these atoms are coupled to the waveguide. So there are some details. They have to be at the distance 2 pi times the wavelength and so on, but these are details. And so what you can do is that you can come with a weak excitation and excite this atom very weakly, such of them that the probability that each of them is excited is very, very small. And now you wait, so you excite them from here to here, and then you wait for the detector and wait here. I'm trying to do experiments like that actually here. So you wait in the detector, and if you detect 1 photon here, 1 photon at the detector, it means that one of the atoms has made this transition. But since you don't know which atom it is, then you will have an entangled state. And so if you want, since all of them are coupling the same wave to the fiber, then the dynamics has to be a superposition of all of them. And if you look at that, then you see that what is the probability of error? The probability of error, this infidelity, is related to the fact that maybe you created 2 excitations. So your laser pulse is too strong, then you will have here 2 atoms excited. In fact, you have a linear superposition of 0, 1, 2, 3. So your intensity is very strong at the beginning, the one of the pulse laser at the beginning. Then you may have 2 excitations, and if you detect 1 click here, then you will think that you have created 1 excitation, but actually you have 2 excitations there, so you're making an error. And in fact, the success probability, unfortunately, is also related to this epsilon. So actually it's 1 over epsilon, because if you don't want to have two excitations, do the excitation very small, but then the probability of a single excitation is also small, so most of the time you have 0 excitation. That's why there is this trade-off. The infidelity have to be small. The success probability will be, actually this is proportional, that's wrong, it's epsilon squared, so it will be also very small. But this will create one excitation, but actually you could repeat it. So what you could do is to, do this. If you detect one photon, then you know that there is a collective excitation. Then you do it again, and if you detect again one photon, you have a second collective excitation. You can load one by one your excitation. This was like the loading your gun. And once you're done, then you can throw the pistol. However, so the probability for this process to be successful is the probability that the first excitation is loaded times the second excitation, because it's in the middle. The second time that you repeat, you don't detect a photon, then you have to start from the scratch. So the probability for this to be success is the product of the probabilities. So it's some number to the power m. So it's epsilon to the power m. So it would be exponentially small with the number of photons. So in practice, you want to have an error, let's say, of 0.01. It would be 100 to the number of photons, so you can put maybe 3 photons or something like that. So that's not the scheme. That's why we have to, something different. And so we have studied many ways, and there are many ways of doing that. And just want to give you what is one of the possible ideas. Well, the idea is to get rid of the errors that were present in this method of repeaters due to the excitations of 2 photons or the no excitation, which gave rise to this trade-off of probabilities. And you can do that just by using one of the atoms themselves as the generator of the photon. So you excite only one atom, which is somewhere else. It's here. You excite this atom. Then at most there can be 1 photon. So you know that then there will be no errors in which there are 2 photons. On the other hand, it may happen that sometimes this atom, instead of emitting the photon in the waveguide, it emitted somewhere else. So there is no excitation. So maybe you think that there was an excitation, but there is no excitation. Or maybe the photon is absorbed in the fiber. So before we had this detector, which heralded the fact that there was some excitation in your ensemble. So we need some heralding here. And the best thing is to use the atoms themselves to herald the excitation. So you take another atom, which actually it turns out that could be the same, that would herald later on that 1 photon has been loaded. So you create at most 1 photon, and your detector, if it clicks, it means that 1 photon was heralded and was absorbed by the fiber. And with that, you get rid of the error. So that's typical scheme that you can see. So you start with all the atoms in level S. Then first you excite your atom, your source atom. This will create an excitation. You don't do anything, just wait. And maybe these states here got the excitation here. Hopefully it's here, but you don't know still the collective excitation. And now what you do is that the atoms in a second step, in the atoms that are here, you excite them with a laser and then wait. And with this atom here, you wait to see whether these atoms emit another photon, make a transition in your detector, and therefore your detector change the internal state. In other words, if at the end your detector has changed internal state, the only compatible process, the only way that it can have a different internal state is because, first of all, the first atom created a photon, and second, the second ensemble created, absorbed the photon, created the excitation, and emitted it again such that it can come to the detector. And with this, you can prove that the error is 0 in this scenario. Of course, there will be errors related to magnetic fields. There will be errors related to whatever. I don't know, maybe just not populated the whole state and something like that. But they say these main errors will be exactly 0. So with this method, you indeed get that the error is 0. So whenever you detect 1, there is no error at all. And the probability has a kind of nice scaling, because it scales, so of course, if these atoms that are here have to emit the photon in the waveguide, and the probability for that is this Purcell effect. So it has to scale with the Purcell effect. So it will be something like 1 minus 1 divided by this Purcell effect. Actually, the square root of the Purcell effect. But still, if you want to load more excitations, you will have to repeat this process. Then you will have to be successful the first time, successful the second time, because it's in the middle. Sometimes you're not successful. Then you will scramble the state, and you will have to start again. So still, there is a probability of creating m photons, which scales exponentially with the number of photons. But this will allow you to, when you put some numbers, you can go to 10 photons, 20 photons like that. And now, just to finish, there is a way of getting a polynomial probability, and that's basically keeping in memory the excitations that you have. So whenever you create an excitation, you don't try to create an excitation on top of that, because if you fail, you will destroy the one that you had. You put it in some other level. And just by doing that and some tricks behind, you can get the polynomial scaling. So that's a summary in which you have the different methods. And so I think that I'm basically finished now. I wanted just to say that we have also studied in this system the process of self-organization, very much like the one that Helmut studies here. So how these atoms interact in the fibers, start emitting, interacting with each other, they will move, and then they have to create some structures. We have also studied quantum simulations in this system. So actually by putting, by designing now in 2 dimensions these dielectric crystals, these photonic crystals in some particular way, you can get Hubbard models in which the distance between the potential wells is not limited by the wavelength, but is limited by some other, by the Casimir-Polders forces, and it could be of the order of, yes, 50 nanometers, the distance. And so this means that automatically in your Hubbard model, you increase the energy scales by a distance. We call like the distance square. So you could increase the energy square by a factor of 100 or something like that. And also spin models. So by using now what I mentioned before, that the atoms that are coupled to these bound states can emit a photon into the band gap, which is absorbed virtually by some other atom. This gives rise to some dipole-dipole interactions. And we predicted dipole-dipole interactions of the order of the gigahertz in the gigahertz regime. So it could be huge dipole-dipole interactions in this system. So we have been studies on how to design some particular models with that. And we have also now worked on surface acoustic waves, but I think I'll stop here and summarize. So I was talking about a system that is relatively new. It's new for me. I mean, it's not new because there have been experiments and people thinking about that and making proposals already several years, which is to change a little bit paradigm that we want to have atoms as far away as possible from surface, but just put them very close to surfaces, because they can use properties of this interaction with the surface itself. This can give rise to very strong couplings, and these strong couplings can give rise to new regimes which are difficult to get without these new couplings, and to funny behaviors. I mean, one of these funny behaviors was this existence of these multi-photonic bound states, but I'd say that it could be also implemented with atoms in optical lattice, nevertheless. And but also, I mean, from the theoretical point of view, you can think about describing some situations which are new in the context. These are the ones where you have retardation and dispersion relations which are nonlinear, and so this gives rise to this method, path integral-based method, that for me was something that I learned and I like it very much. And also, there are applications in the creation of multi-photon states, and the one that I mentioned in quantum simulation. Of course, the difficult part here is these are very challenging experiments, but people are trying, and I hope that in 3, 4, 5 years, some of these ideas can come to the lab. Thank you for your attention.
So thank you very much, Ignacio, for the nice talk. Now I would like to ask you for questions and be a bit patient to get the microphone before you pose the question so that we record it also. So please, questions? Yeah.
Ignacio, I'm more familiar with these first methods you had. You talked about the theory methods, the quantum optics part. But these path integral methods, how do they scale with the number of particles? I have no idea how this works.
Okay, so the number of photons, they don't care about the number of photons because they are integrated out. It's like in quantum optics, that if you have a coherent state that is very strong, it doesn't make it more difficult to solve your problem. But the number of atoms. But for the number of atoms, there's an exponential scaling, but also for the input-output formalism. So when you have to solve a master equation with an atoms, then the Hilbert space is 2 to the power n. So you'll have to solve actually with density matrices with 2 to the n times 2 to the n problem. And here it happens the same thing. But the main additional difficulty that you get is not that the number of equations grows, is that these equations are not local in time. So namely, the derivative of some several of your atom at time t depends on the state of the atoms at t minus time, integrated over time. And of course, this is what used to happen when you have retardation effects. Okay.
But what do you gain?
We can't describe the experiments. If you do these experiments, I can predict what will happen.
Okay. More questions? Maybe I ask one. So Ignacio, for the proposals on having the quantum emitters near the waveguide, I guess some implementations are having these atoms trapped in evanescent fields or so, and in there, of course, will be relevant the position. And so far, you were assuming the mass to be infinite. Could this be also something useful that you could use also to entangle the motion and so on?
Actually, it can be very useful. So in one of these, in order, I didn't explain that in detail, but in the polynomial scaling, so in this a probability that scales polynomially with the number of excitations. In this method, actually, in order to store the excitations and then merge them, so you would like to store one excitation, then you create another excitation, then you would like to make out of this excitation 2 excitations on the same internal state, and then you store another one. You do it naively just by just merging excitation, they still get exponential scaling. So you can show that there is a method in which if you have logarithmic of m internal states, then you can store m excitation in a polynomial time. But so you have m equal 10, that's okay. But if you want to have 1,000,000, let's say in 100 generations from now, then because you would like to have logarithm of 1,000,000 internal levels, and I don't know any atom that has that. However, the atoms have motional state, and by that time they will be so advanced that they could be able to handle the motional states, and since there are many motional states, then they could have handled 2D states in order to have polynomial scaling.
More questions? If this is not the case, then maybe, okay, very good, Francesca.
You are so fast.
No, just.
Okay, so I have a question regarding to the bound state. So you kind of propose 2 physical realizations. So the first one with the fiber, a waveguide, and the other one with optical lattice. And in the first case, I don't know if I got really the point. You mentioned that the dispersion can be shaped in such a way that is a delta function.
Well, what happens actually is that for any dispersion relation, that is, I mean, it cannot be infinite. It cannot go from minus infinite to infinite. But if there is a dispersion relation which ends something,
yeah,
then what happens is that the photons that are here, they will propagate. So if there is no atom, they will propagate according to this dispersion relation. So if they're in the linear part, they will propagate like a wave packet. If they're in the dispersive part, they will disperse, and so on. So that's the normal, dispersion relation. That is a single particle problem that we understand. Now you have the emitter. So what is the emitter doing? So one of understanding what the emitter is doing is that it's creating a perturbation on the propagation of the photons. So it creates like a potential. So the emitter itself creates like a potential to the photons. So now the photons, instead of feeling free in the fiber to go through because there's nothing, then all of a sudden they see an emitter, and the emitter is like a delta potential, like a step down and up. And this potential, this step up and down for the atom, for the photons, then can have a bound state of photons. And so the potential is created not by the dispersion relation itself, it's created by the fact that you have an atom. The atom creates a a potential, and now this potential has a photonic bound state. And now you can start collecting photons. You could have, photons there, and these are the bound states.
Okay, and then basically my question is what is done the equivalent of this delta potential in the case of the atom in the lattice, because it doesn't look me so easy that you can get the same, but this was a key ingredient in the first realization.
Okay, so maybe in the atom picture is simpler to understand or more difficult, I don't know. So imagine that you have only one internal state and you have your atoms in optical lattice, and they can propagate in the lattice, they can tunnel, right? And they will move through. So you put a wave packet, then it will move, and it will go from place to another, and there will be no bound state there because it can move. The wave packet can move in your lattice. Now imagine that in the middle, these atoms can be promoted some other internal state, which is trap. So when they are going through the lattice, at some point you have a laser just pointing here, and then they can be promoted to some other internal state where you have a bound state. And of course, you could just make oscillations, for example, there. When you're here, make some oscillations and go back. But imagine that this laser now is very far off resonance. So you really don't excite your atoms to the other side state, which is trap. Still, this will affect you. So you will have kind of virtual transitions of your atom to the other internal state and coming back. And this will renormalize the motion of your atom when you're close to this. Where the atoms that are moving in the optical lattice, because of the laser, they will see a renormalization somehow of this motion. And this renormalization turns out that they see a potential. And so they can fall in the potential and stay there. And so they will be then trapped in this potential.
So the theory that you developed for this exact solution seems very powerful, no? Can this also be applied for some other system, or?
Well, the whole trick, that's something that, I learned, I didn't know, but the whole trick is that if you can write a very complicated Hamiltonian, which has 2 degrees of freedom, like say the atom degrees of freedom, the photon degrees of freedom, and the Hamiltonian is quadratic in creation and annihilation operators or linear, like it happens with the QED Hamiltonian, then yes, because then what happens is that you write these path integrals, and then you can integrate out the photons. You will get a complicated problem, not local in time, like that, for the atoms themselves. So as long as this happens, this will be true. I mean, this is something that we didn't invent. That was invented by people in condensed matter, but they, as far as I know, they don't apply to real-time evolution. They apply to finite temperature systems. They eliminate, and actually, this is the method that people apply in lattice QCD, but they do the other way around. So when people solve problems in high-energy physics, that they have fermions, matter, and gauge fields, what they do is that the fermions interaction in the Young-Mills model or whatever Young-Mills theory, the theory is quadratic in fermionic degrees of freedom. Of course, it's difficult because they are coupled to gauge fields, but otherwise it's quadratic. So you write it in terms of path integral that you can integrate the quadratic theory because it's Gaussian and get the theories only for the bosons. And then at the end, you only have to simulate bosons which don't have the sign problem. This is where they use quantum Monte Carlo simulation. So that's very widely used. I mean, the idea is to use it in this problem. This is in quantum optics.
Thank you very much. Some more questions? Okay, so if this is not the case, now we have some coffee and pastries for all of you, and you will also be able to ask more private questions to Ignacio. So let's thank him again very much for his
private.